All right, so the condenser, you can see it. It's just below the stage. It's this little column here. Its job is to focus the light. You can see there's a condenser adjustment knob. It's on the opposite side, underneath the stage. Excuse me. Sorry. Opposite side from the stage adjustment knobs, right? So that one you can raise and lower. Yeah, go ahead and plug in and turn on your microscopes. So that you can see the light shines from the bottom. If we follow the pathway of the light from the lamp through this condenser, you can see, of course, we have lenses to focus the light as it goes from the specimen on the stage into our eyes. We also have the condenser has lenses to focus the light that illuminates the specimen, right? And so you can raise and lower that. It can help create contrast that makes an image easier to see. If an image is too bright, that can help by, you can move it away a little bit. There's also something called the iris. If you look at the condenser, there's a little lever on the front of it that you can rotate, and if you look at the light shining up through it, that can actually control the amount of light. That's called the iris. A lot of those things work the same way as the iris in your eyes works to constrict your pupils on a bright, sunshiny day. Does that make sense? So, yeah. So you're using it correctly, right? And if you look from the side, you can see that the amount of light as you do that, right, as you were just doing that,
so this
the amount of,
and this is the iris.
yeah, so this is the condenser going up and down, and as you wiggle this, that's the iris opening and closing.
Okay, and this one is the iris too?
Oh, so that, there is a little blue filter, and that brings in some things, right, that I'll talk about. You can see here there's an angle of the light focusing on the specimen. That angle actually has something to do with the ability of the microscope to see light. So here are some nice light microscope images. Here are some rules before we go on. Laws of physics, basically, that govern how microscopes work, right? So certainly, the multiplicative property of using lenses in line with each other, right? That's a property of physics, that you multiply the magnification of the two lenses, okay? So along with magnification, right, the purpose of a microscope, of course, is to magnify, but without an increase in resolution, magnification is useless, okay? So here I have two images. One is magnified to twice the magnification of the other, but you can see that this one doesn't really provide much more information. Unless you're really far away, it doesn't help to make this bigger at all, because if you can see the picture, it's as much as it is bigger, it's also blurrier. Can you see that? That's because we've magnified without increasing resolution. You understand? So the best comparison I can think of in this modern day and age is when an image that you blow up on your computer screen, and when you blow it up, it becomes what we call pixelated. You know what I mean by pixelated? You can start seeing the little pixels that the image is made of as you zoom in on the image, right? So when you magnify and you see things become pixelated, that's evidence to you that you've magnified without increasing resolution, right? So resolution is a measure of distance. It is a measure of distance between two dots. In the case of digital images on your computer, it's the distance between two pixels, right? Or the size of the pixels, basically. Make sense? In the terms of a microscope, it's being able to tell two dots as two dots and not one, right? It's the boxer's test, right? The boxer has been boxing for 11 rounds. He's about to go in for the 12th round. He's been taking a beating. His trainer will say, how many fingers am I holding up, right? He's holding the fingers right in front of the boxer's face. The boxer, though, it's not a question of his ability to magnify the fingers. He has to differentiate how many fingers there are. Does that make sense? So, how many dots is this? Clearly 2, right? That's easy. If I moved it closer together, the 2 dots, it would be harder and harder to tell whether it was 1 dot or 2. You agree? Right? So resolution is the minimum distance you can differentiate and say with correctness that what you're looking at is 2 dots and not 1, is the distance those 2 dots are apart. Well, what does that depend on? It depends on a couple of things, and one of them is pretty important. That's lambda here, is the wavelength of light. So as it turns out, light itself is a limitation on our ability to magnify images, right? In the same way that making slices of bologna, the thinness of those slices is dependent on the sharpness of the knife that you use to make those slices, okay? So, well, what about the sharpness of waves of light? Waves of light have a wavelength. You've heard of it, right? So the wavelength of light goes from 400 to 700 nanometers. Can you convert that into micrometers? How many micrometers is 400 nanometers? 0.4. How many people got that right? If you got that right, you're doing great. If you didn't get that right, you're not doing terrible, but yeah. Does that make sense? Nano is billionth, 400 billionths divided by 1,000, 1, 2, move the decimal point 3 points to the left, 0.4 micrometers. Got it? What about bacteria? How big are they? About 1 that I said before, right? Can we see bacteria with a light microscope? According to this, right, the wavelengths of light are smaller than the bacteria. We should be able to see one, right? What about viruses? Viruses are about 0.1 micrometer, right? 1/10 of a micrometer. Where is that? Right? 100 nanometers. So they are smaller than the wavelengths of light that we use to look at them with. How can we possibly see them? How can we possibly make slices of bologna thinner than our knife is sharp? Does that make sense? Okay. So as a result, we can't look at viruses in a light microscope. Do you guys know what kind of microscope we use instead? An electron microscope. We'll talk a little more about that on Thursday. Okay. Lastly, a couple other properties. We're going back to this resolution equation. You do not need to know this equation, by the way, but I use it to further my conversation about what is needed for seeing things in a microscope, right? Along this D is dependent on the wavelength, right? Resolution depends on the wavelength of light that you use to illuminate with. It also is dependent on this thing n sine alpha, which is the numerical aperture, right? This has to do with the half angle of the cone of light. So we talked about this cone of light. Where is that picture? So this angle of the cone of light that we use to illuminate the image, it's also dependent on this n. N is the refractive index of the substance that we're viewing the light through, right? So light travels through media, right? It travels through air, comes out of the light sources, bounces off the floor, and hits us on the eye, and that's how we see the floor, right? if we use a different medium, to look at light through, like water, we'll notice that the light doesn't behave the same way. Right? I put the grease pencil in water, and you can see it looks bent, doesn't it? It looks like it's a little bit broken. Right? And that's because when light passes through water, it changes direction a little bit. It changes the angle at which light goes, bends a little bit. It travels through water differently from the way it travels through air. The refractive index of a vacuum is exactly 1. Air, slightly more than 1. Water, 1.3. If we shine our light through a diamond, it would bend even more. Right? And that's why you get the prismatic effect of a diamond, right? When we use the oil immersion lens, the reason we use that is because this 100x lens on your microscopes, the reason it works is because this oil bends light. It has the same refractive index as the glass, right? So immersion oil, I guess I don't have it on here, but immersion oil should have the same refractive index as the glass that our lenses are made out of. And that will minimize the amount of direction changing that our light does as it passes from the specimen to our eyes. Okay? So we'll talk about, I'll interrupt you guys a little bit as you look through the microscope. I'm going to give you some stuff to look at right now. I'll give you, in fact, I want everyone to come up and grab something from one slide from one of these trays that I put out here, okay? So that includes Giardia. Anyone heard of that one? There's yeast. There's Rhizopus. Here's Trypanosoma. This causes African sleeping sickness. What else we got here? These are bacteria. Here's Rhizopus again. Candida albicans. Anyone ever heard of that one? Oh, here's amoeba. You guys want to look at amoeba? Amoeba? That's pretty good. So inside there are slides. Take one slide. Oh! That was dumb, huh? Sorry. Any of them break? One broke. That's on me. Oh, wow, I got lucky. Better lucky than good. Okay, thanks. Sorry about that.
Be careful, you have some broken here.
Oh. Yeah, I see that one sliver. It came from, thank you. Thank you. Just take one slide. One slide that interests you. Okay. Phew. How's it going? Any luck?
Yeah. Just want to know if that is looking the right thing. East, I think the long one.
Oh yeah,
Only
good.
one?
Oh, you mean the long one on the right side?
Yeah.
That stringy thing on the right
Yeah,
side?
yeah.
No, 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 no. So that's probably an artifact. That's
Oh.
probably like a piece of dust or something.
Okay.
Let's.
So how would...
So the little tiny flecks, yeast are really small. The little
what
flecks
shape,
you
like
see all over.
all over?
Yeah.
Dots? Okay.
Let's see if we can get a better picture of that. Yeah, so all of it looks like it's stained purple. Are you looking, you're looking at oil immersion. Can you see anything?
Well, yeah.
Oh, look at that. Okay, so you might see that better if you got some immersion oil, and that's over here. That's, if you do that, make sure to clean off the immersion oil. How you guys doing over here? Any, what do you got? Anything good? Oh. Okay, so they look like little mushrooms, don't they? Those are fungi. And those are their little fruiting bodies where their spores come off. Good. Anything else? What's that? Nothing. Okay, nothing doing. Oh, did you guys sign out your you did. Everyone did, right? Sign out the microscopes?
No.
Okay, so not a big deal, but you should sign out when you... So you're right, I'm not seeing anything in here. So the trick is, first of all, always start with low power. And then my trick is to bring the stage all the way up to the as close as it can get.
Okay.
Once that's done, right? Low power, bring it up all the way. Once it's up all the way, then focus is either there, right? And I don't see a lot, or focus must be down.
Okay.
Does that make sense?
Right.
So I look in and I turn it down until I see something, okay? So it's all the way up, look through, and as you look through, turn it down until you get something in focus. Ah, so you can't do that while you're not looking.
Right.
Look at the same time. I'm sorry, I shouldn't.
It's okay.
Yeah. Okay.
I see
You good?
like a couple black dots.
Let me see. Oh yeah. So try to get those little black dots in focus, right? Those are probably little Giardia things. So ladies and gentlemen, if you want to share with your classmates, you can. What you should never do is push the microscope from side to side on the counter. If you do that, it's a precision instrument. Just like a wee little babe, violent shaking is bad for both, right? And as you push it across, you can hear it vibrate and rattle, right? So it's not going to break anything immediately, but if you shake things enough, then you'll mess things up. So if you want to share with people, you can either rotate the headpiece or just pick up the microscope and then put it down. And either of those is fine, okay? Okay. Yes.